Okay, this is a mini review session for the fall exam for the Pre-Cal 2 Calc A class. This is not going to be um, covering entirely every single topic because that would take way too long. I'm going to try to be very concise um, for absolute, going over everything. You should look over all of the past notes and all of the past tests and all of your past homework questions. That is what is covered on the exam. But this is something that's supposed to be brief and hits all the highlights, most of the highlights. Okay, so right here I have written down the 6 major units that we covered in class so far. And we're going to focus on these one at a time. Functions and graphing. This was the very first thing we did, and this is just a huge topic. So some things to remember: even and odd symmetry, domain and range, and the rest of what I have listed up here. So for even and odd symmetry, I'm just going to show you 2 examples. One of these is even and one of them is odd. Okay? Um, the F will be even and G will be odd. With even and odd symmetry, to test for that, you replace X with negative X um, and examine what you get once that is finished. If you end up with the original function, then that means even. And if you get the exact opposite of what you started with, then that means odd. Okay, domain and range. For domain, there are 3 rules, and I am going to take the time to write those down. One is do not divide by 0, and these are all do nots. Everybody else is okay. Do not divide by 0. So, for example, 1 over x minus 1 has a domain of all reals other than x equal to 1, because that would make you divide by 0. No even root of a negative. No even root of a negative. So, for example, the 4th root of 3x plus 1, that has a domain. 3x plus 1 has to be greater than or equal to 0. 0 is okay here. You're allowed to equal 0, but you cannot be negative. So this would be x has to be greater than or equal to negative 1/3. The third rule is for logarithms, and I'm going to go ahead and go over that now. But no log of a negative number or 0. Okay, so for example, say you have the log base 2 of 5x plus 1, then 5x plus 1 must be greater than 0, not greater than or equal to, just greater than, and x is greater than negative 1/5 then. Okay, those are your 3 domain rules. The ranges are just case by case. They're a little bit tricky. You should know your graphs to know your range as well. And intercepts, know your x and y intercepts. How do you find the x-intercept and the y-intercept? So for example, say g of x is x squared minus 4, then to find the x-intercepts, you replace y with 0 and solve for x. These are also known as zeros, and they are also known as roots. We have several names for the same thing. Those are all x-intercepts, and then the y-intercept would be negative 4 there. Also, we have transformations of functions. So in general, say you have y equals a times f of bx plus c plus d. Um, all right, so this would be a vertical stretch. The b would be a horizontal stretch or shrink. Um, C and D would make you move up and down and left and right. So this is up or down D, and this one here is left or right C. And remember, when things happen inside the parentheses, like the C and the B do, it happens in a reverse manner. So for example, f of x equals negative absolute value of 2x plus 2 plus 2. This would reflect over the x-axis. That's because of this negative. So you also have reflections. It has a vertical, no, a vertical shift up 2, a horizontal shift left 2, and a horizontal shrink by a factor of 2. And the graph of that would end up looking like this. Yeah. And your slope, its absolute value of x has slopes of 1 and -1 usually is 2, which is the horizontal shrink of 2. It also could be considered a vertical stretch of 2 because you could factor it out. Makes the slope 2. Okay, and combinations of functions. For combinations of functions, you will be given two functions, say f equals 2x plus 1, and g equals cube root of x. What is f of g? And what is g of f? You also would be asked to add them and subtract them and multiply them and divide them. And then usually when you're asked to divide them, I would ask you for the domain as well because we care about dividing by 0, of course. Then the last topic is inverses. On inverses, lots of things are happening there. Essentially, an inverse to a function is the other function who does the exact reverse process. So for example, for the function f of x equals x minus 1 cubed, the reverse process, or the inverse function, would be f of x equals cube root, f inverse of x equals cube root of x plus 1. So these are reverse processes that one function does to x one thing and its inverse will do the exact reverse thing. So what happens here is domains and ranges will switch. Graphically, they are symmetric over the line y equals x. And to find them, if given a function to find the inverse, you would switch x and y, solve for the new y, etc. Okay, next topic is quadratics and rationals. Okay, so starting with quadratics, you have to understand how to get something in standard form. So if we have y equals ax squared plus bx plus c, this is not standard form, but standard form would be a x minus h quantity squared plus k. You can complete the square to get it into this form. It is very important to know the vertex of the quadratic. It is hk when you're written in standard form. The axis of symmetry is always x equals and then whatever the x coordinate of the vertex is. And so for example, suppose y equals 3x squared plus 6x plus 5. You can work on that, but I would ask you to find the vertex. It's -1, 2 once you do it. And the axis of symmetry will be x equals -1. So how you find the vertex is up to you. You can put it in standard form, or you could use the formula that h equals -b over 2a is always the x coordinate of the vertex. And or you could complete the square. Okay, then we also have in this section, well, solving equations, yeah, complex numbers. So for complex numbers, remember the standard form of a complex number is a plus bi, and I, remember, is the square root of -1. That is the imaginary component, and a is the real component. We're going to do more on complex numbers at the end of the year. But here's an example. Put this number 2 plus I over 3 minus I in standard form. That involves multiplying by the conjugate. I believe that the answer will end up being 5/4 plus 5/4 I when you're done. Okay, and then the last topic I want to talk about here is the rational functions. So to do that, I'm just going to give you a rational function example. This is x squared plus 2x minus 15. And I'm going to come back to this later on when we do limits and infinite limits and when we talk about continuity. So it's a good, we're going to see this come back over and over again. This, I'm going to go ahead and let you do all of the work, but I'm going to give you the answers. I would ask for all sorts of things, but the x-intercept is um, -5. The y-intercept is 15/9. And actually, this is really a point. Okay. The horizontal asymptote, that's a line, and that will be y equals 1. And the vertical asymptote here, there's only one. It is x equals -3. This also has a hole. Later on in calculus part, we'll talk about a hole being a removable discontinuity. That coordinate should be 3/4. And there is no symmetry. These are things I expected you to be able to do and solve for. And then you would have to graph it all. I do have a little mini graph too. You remember when you graph, plot your intercepts, or sorry, yeah, intercepts and your asymptotes and your hole. So this is just a sketch, a rough sketch, but I believe this is what it should look like. All right, moving on. Exponentials and logarithms. You have to, absolutely have to know the graphs of these. I will tell you there is a graphing part on the exam, and definitely these will, at least one of these will be on it. So you should know what a to the x looks like. There is a horizontal asymptote at y equals 0. The point 0, 1 is on there, and this is your general shape. Notice the domain is all reals, and the range is 0 to infinity, not including 0, only positive numbers. The converse for this is y equals log base a of x. In log base a of x, these are inverses, by the way. We do exponentials and logarithms always together because they're inverses. And so a horizontal asymptote will invert to a vertical asymptote, right? This was x equals 0. Nope, that was y equals 0. And that when you switch x and y, that will switch to x equals 0. And the point 0, 1 will switch to 1, 0. And then the rest of the graph looks like this. Notice this is the domain restriction. X has to be greater than 0 there. Then the range is all reals. Also, wow, the domain and the range switched. Okay, that always happens with inverses. So be sure to be able to graph exponentials and logarithmic equations. Know the properties of both. Oh, by the way, these are only for a more than 1. When a is less than 1, we don't have increasing functions, we have decreasing functions. The shapes are the same, but they would actually flip over the axes. And you can look those up if you want to. Okay, properties of exponents. I'm just going to give you a couple of basic examples. Remember that when you have the same base and they're multiplied, then the exponents will add together. Similarly, when you're dividing, the exponents will subtract. Anything, not absolutely anything, but any non-zero or not any non-zero number to the 0 power is 1. Let me think about those. So then conversely with logarithms, we use this a lot, but the natural log of a product is the sum of the natural logs. Also for division, and we use this when we are doing derivatives because it makes the derivatives of logarithms much easier. And this could be log base anything. I'm just happen to be throwing up log base e. Also, the natural log of 1 is always 0. Oh, there's another property here that the log base, I don't know, anything of, say, x cubed, the 3 will go into the front. So this is an example. And there might be more properties. You need to go to chapter 7. That's exponentials and logarithms. We pretty much did that whole chapter. So there are lots of good examples that you can look through in the book there, and odd problems that you can do with solutions. And one of the most important things about exponentials and logarithms is the definition of a logarithm as the inverse of an exponential. And so if y equals a base b to the x, then written in logarithmic form, this is log base b of y equals x. All right. And so this is how you convert between the forms. So for example, and there are a million of these examples, but I know that 2 to the third power is 8. And written as a logarithm, this same idea is that the log base 2 of 8 is 3. And so it's how you solve for an exponent. It tells you, oh, equals the exponent. And then the last thing to do with exponentials and logarithms is to solve equations. And there's a lot on solving equations and a lot of details that go into that. So I really encourage you to see Chapter 7, examples and practice problems there. Okay, I would even maybe rewatch it or rewatch the whole video. You have to get your hands dirty here and do some practice problems. Okay, the next topic is trigonometry. And this was our final pre-calculus topic before we started talking about limits and derivatives. So with angles, lots of things with angles. Coterminal angles, reference angles are probably the most important in that list of things to do with angles. Make sure you can convert between degrees and radians. Remember, 180 degrees is pi radians. Pi, by the way, is the number 3.141592626 or 265. Anyway, so that's just a number. Okay, pi, it's a number. And that many radians is equal to 180 degrees. And that's how you convert back and forth. I'm going to just cover a few basic things. First of all, standard form of an angle is really important. On the XY axis, we plot angles. We just put them on top of an XY axis. And then we make this XY axis measure angles by saying the positive x-axis is 0 radians and 0 degrees. This positive y-axis is 90 degrees up, right? It's at a 90-degree corner there. So we go 90 degrees up. We always go this way for the positive direction. Then we would have 180 degrees and then 270 degrees. The way we put an angle in standard position is we place one of its sides along the positive x-axis, and then the other side will land wherever it is. So for example, 300 degrees would land here. This is 300 degrees. That leaves you 60 degrees until you get back to the positive x-axis, do a full 360. And so we have this amount left in here, which is 60 degrees or pi thirds. This, by the way, would be your reference angle. Remember, reference angles always go to the positive x-axis. I didn't use 300 degrees and pi thirds for no reason. That is one of our common angles that you have to be able to evaluate all 6 trig functions at. And the sign will be different based on the fact that it's lying in quadrant 4. I will typically put in a right triangle actually onto the XY axis, and this will help me get my sign right. You always use the x-axis as one of the sides of these triangles. The reference angle will be in the corner there right by it. And then you have to know your triangles. That's what I do. So this is a 30, 60, 90. This would be 1, 2, square root of 3. And then because I'm on the xy plane, I can see that 1 goes in the positive x direction and radical 3 goes in the negative y direction. And so now that I have the sides of this triangle, I will use SOHCAHTOA, and I can evaluate the sine, cosine, and tangent. And then I will reciprocate those, and I could evaluate the cosecant, secant, and cotangent. And you need a lot of practice doing these. I will be asking these questions any 6 trig function of any 30-degree, 60-degree, 45-degree reference angle, because you also have to know the 45, 45, 90 triangles. The other thing that you have to know, and then also, so be able to do the signs. Some people don't do what I do here to get the sign right. So for example, the tangent of this is 30 degree or 300 degrees, which is that 5? No, yeah, 5 pi 6. The tangent of 5 pi 6 is the opposite over the adjacent, so that would be negative radical 3. And I evaluate that with the signs just like that. A lot of people just use all students take calculus. So the C means that only cosine is positive in the 4th quadrant. Everybody else gets a negative sign. But also if cosine is positive, secant is positive too. So you got to know those reciprocal identities. All right. Then the other thing you have to know are the axis angles. The 0, the pi halves, pi, and 3 pi halves. I do this with a unit circle. I think of a point, a distance of 1 away from 0, 0. This point here is 1, 0. This one is 0, 1. Here I have negative 1, 0. And the last one would be 0, negative 1. The x value, the x coordinate, is the cosine. The y coordinate is the sine. So for example, what is the sine of pi? Well, the y coordinate there is 0, so it is 0. And then you can get tangent by doing the ratio of sine over cosine, and then you can get all the other 3 now. All right, so be able to do this. This is on there. The final, we're going to talk about graphs too, but before I talk about graphs, I want to talk about inverses. You have to know how to do inverse trig functions. And so essentially what you have is a trig function. You insert an angle, and you get out a ratio, right? It's the ratio of 2 sides of a right triangle. And so that's always how this works. Here, your input, I'm going to make the input blue, is an angle. Angles are blue. So I put into a trig function an angle, and then I get out a green ratio. So that would be like 1/2, or, opposite over adjacent, whatever those happen to be. So you get out the ratio. The inverse is the function that does the reverse of that. So the trig function inverse, of, well, now we're going to switch them. So now I input the ratios, and I get out the angles. Theta, angle. That's the answer. So it's the question of, all right, so for example, suppose I took the sine of some angle theta, and I got, I don't know, negative 1/2. Well, the inverse sine of negative 1/2 is supposed to tell you what the angle was. And so to figure that out, you have to know what I just talked about previously. It's 30 degrees is the reference angle whose sine is 1/2. And I just know that because I have those memorized, and you have to know those. I know that 30, 60, 90 triangle really well. But that's the reference angle. So 30 degrees is the reference angle. So that's pi 6. And then we've all agreed, maybe some of us forget, but we've all agreed that the answers to inverse sines, because technically there are infinitely many angles who give you a sine of negative 1/2. But we've all agreed to put the angles here between negative pi halves and pi halves. And so this answer is going to be negative pi 6. So be able to evaluate these as well. Be able to evaluate those as well. Last topic with trig is graphs. So you have to know the graphs of the 6 trig functions. And then you also have to be able to shift them, reflect them, and find the period and the range. So we've covered those, a lot of those. Let me just give you an example, I suppose. The sine of 2x minus pi plus 2. So you could graph that if you wanted. The period is now just 2, or sorry, pi, just pi. The period would be pi. You get that from 2 pi over 2. That's your period. And then you're going to adjust your x-axis when you graph it so that the period is pi. You're going to go right pi halves. That's your phase shift, and up 2. So you can graph that out and work that out on your own. All right, now we're getting into calculus. Limits. We're going to evaluate limits graphically and analytically, do sided limits, and talk about continuity and the definition of the derivative. So graphically evaluating limits, just if I were to have some sort of graph here, remember the question is, do the roads meet up? So if this is 2, and see I have a hole here, this 2 will have a limit. The limit as x approaches 2, I'm going to say this is a graph of g of x equals 1, because from the left side and from the right side I got to 1. If I have an asymptote at, say, -2, well, this limit does not exist. The limit as x approaches -2 does not exist, because from the left it's different than from the right. And it's infinity, which is not a number. Well, infinity, so the limit as x approaches -2 from the left here is infinity, and you just can read that from following following the graph, go towards -2 on the left side of -2. You can see that the graph extends up to infinity. So you'll have to look at pictures of graphs and evaluate limits. Then you also have to evaluate limits analytically. So let's go back to that function. What is the limit as x goes to 3 of x squared plus 2x minus 15 over x squared minus 9? The way you evaluate limits is you just plug in the number. In this case, if you plugged in right away, you should get 0 over 0. That does not mean that there's no limit. There could be a limit or there could not be a limit. You have to do more work here. So various things we did, we factored in crossed off. We multiplied by the conjugate. We got a common denominator. There were lots of examples of those, so be sure to be able to do those. Let's talk about sided limits really quickly. What is the limit as x approaches -3 from the right of this function? So this is our rational function that we graphed. At -3, oh, by the way, this answer will be 4/3. I think that was the answer to the y value of the whole. Back when we looked at this rational function and graphed it, there was a whole at 3, because when you factor and cross off, that x minus 3 will cross off. And so when I do the limit as x approaches -3 from the right, I think this is supposed to be positive infinity. But this is one of those ones where you really do have to check the sign of 0. Is it positive 0 or -0? On the bottom, I would have gotten 0 here. And do I get positive 0 or -0? On the top, I think I don't get 0. I get a number. And if I'm approaching -3 from the right, that would be something like -2.9. Squared is not as big as 9, so this is a negative. -3 from the right, -2.9. Yeah, that's a -0. And then you can evaluate the top and figure that out as well. Okay, I went ahead and figured that out. You should get positive infinity. It did work out. Also, with sided limits, you need to be careful. If you have this guy, the greatest integer function, you always need to worry about the side then. You also need to worry about sided limits and piecewise functions. If you have something different from the left and on the right, then you have to, and I do the limit as x approaches 0 from the left, then you use the correct piece. That's all. Okay, that brings me to continuity. We really, to talk about continuity, we talk about discontinuities. There are 3 types of discontinuities, but really just 2 that you need to know, removable and non-removable. Removable discontinuities are holes. They are discontinuities that if you take the limit of the function, you get an answer, essentially, because you got 0 over 0 at first and did the work. That's when you get these removable discontinuities. And then non-removable discontinuities. By the way, let's talk about the definition of continuous. In order to be continuous at an x value, then the limit as x approaches that number of the function is actually equal to the y value there. That's the technical definition of continuous. Graphically, you never lift your pencil off the paper. So if you do lift your pencil off the paper when you're tracing the graph, then that's a discontinuity. Okay. And finally, in this section, I want to talk about the definition of the derivative. That's where we saw this. This is our first introduction into derivatives. We learned that the derivative is the rate of change, the instantaneous rate of change. So it has a lot to do with slope. Slope is change in y over change in x. It's f of b minus f of a over b minus a. When you have derivatives, it's this, but you don't have a change in x. You just worry about the derivative at a point, or the slope at a point. Slope at one point, that's the derivative. And that's f prime of c. And that's your slope of your tangent line. This is the slope of these old ones up here. That's the slope of a line where you've got 2 points. That could be a secant line. But down here, this is a tangent line. So the definition of the derivative is that this is the limit of the difference quotient. So you look at f of x plus h, subtract f of x, divide by h. That's how you get the limit. I would ask you to do these for a few different functions. For example, some sort of small polynomial, like x squared minus 2x plus 1. You already know now that the answer to this should be 2x minus 2, but you will be required to do the limit definition. Then the other sorts of examples you might have to know are 1 over x. How do you do the derivative of that? And when you're doing the limit for this, you would do a rational, you would get a common denominator. Okay, that's the definition of the derivative. Last topic were derivatives, and this is very fresh in our minds. I just want to remember your rules, okay, the difference between the constant multiple rule and the constant rule. So say I have y equals the natural log of 3 times x plus the natural log of 4 minus pi x squared plus pi squared. I'm really trying to throw you off on this one. The answer to this is natural log of 3 minus 2 pi x. All right, so see if you can figure that out. Some of these constants, and I'm just going to highlight the constants. Constant, 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 constant. Some of those green constants are multiplied to x. They will stay there when you do the derivative of x. The other ones, who are all by their lonesome, they have a derivative of 0. The derivative of natural log of 4. Please, it is not 1/4, because it's not an x. The derivative of natural log of x is 1 over x, but it's not varying. It's a constant number. You can type it into your calculator, and it would be, I don't know what it would be, but if it was 2.36, I know you would take the derivative of 2.36 and make it 0. That's what that rule tells you. Okay, you also will be required to find equations of tangent lines. Remember how to find the equation of a tangent line? You're just using point slope form. And for your slope, use your derivative and evaluate it at that x value that you were given. Also, horizontal tangent lines, that means that this derivative is 0. And then you would solve for x. Be able to do second derivatives and third derivatives and fourth derivatives if necessary, but those are just repeated derivatives. So you do the derivative one time and then you do it again. Be very careful with your chain rules. Okay, you're going to have some multiple choice questions in which really bad chain rules are going to be possible answer choices. So when you have a chain rule, so tangent of something, I don't even care what it's of. Well, I do, but later. The derivative is secant squared of that thing. Please don't change that thing. Even if the inside itself is, let's see here. Let's say it's natural log of x. That doesn't change. It stays. I know you know the natural log of x, and I know that you know it's 1 over x, and that's great. Multiply by it at the end of the derivative. Okay, don't replace. If you got that comment, don't replace, and that means you were doing this. You were putting 1 over x inside. Don't. Keep the inside the same. All right, that's all I've got.